Okay, here's a practical which is looking at the conservation of momentum. It's something very similar to what you might have seen or used already at GCSE, and there's another video in the link to this about the GCSE one. But essentially, we're looking to see whether the conservation of momentum holds true with two trolleys. Those trolleys can vary their masses considerably. Each one is 500 grams. Each of these is 500 grams, and they're loaded on the top quite happily. We are going to look at them coming in towards a stationary object. We're going to look at them inbound, and these are inelastic collisions where they join. And then we're going to look at them inbound with an elastic collision, or even two together for elastic collision. Okay, so it's quite straightforward. We have the masses. The masses don't need weighing. They are pretty accurate. However, we do need to work out the velocity of these vehicles. And the way that's done is by using a light gate. We have this that obstructs the light. And as it obstructs the light, you'll probably see a light that disappears and then comes back on. That gives this motion sensor a chance to time how long it's taken for this distance to cut through the light. If you know a distance and a time, you can interpret that directly into a velocity. Distance divided by time is velocity. So rather, you could, if you wanted to, take the time, and it will give you the time, and you do the sums, or the box itself will do the sums for you. Let's get the box to do the sums for you. When you turn it on, it says select mode, so you press S for select. Time interval, no, we don't do it longhand. Press it again, we want the speed. Enter. It says select the number. Well, that means how many times do you want to take it off here? Select S once, twice. Enter. What's the mask size? This is the mask size across here. We cut those accurately to 10 centimetres. So you press S, and you keep pressing it until you go through to 10, enter, and then it says ready when go. G. So what you do is either of these move through, that one moves through, and once it senses both, it says D, press again, it tells you what the speed of one was, the other one was, and then it gives you selection G, you can go again. Really straightforward. Inelastic collisions are the way to start first. This is a quick sheet to help you pull this together. It shows you the type of collision car 1 strikes car 2. They both move off together after that. Because this is A-level, when you don't want to be too prescriptive, you can choose the masses yourselves. We know the length of the card. Timing gate, I said we could leave that bit because the computer itself will do that bit for you. You just want to look directly at the velocities. Then we work out the momentum before, the momentum after, in each collision. This is experiment 1, of course, stationary target. Experiment 2, moving targets. And then we want to see whether the kinetic energy before equals the kinetic energy afterwards. Is kinetic energy conserved in these collisions? I'm sure I don't need to remind you how to work out the momentum before. You merely take the mass. Let's write this down. So the momentum is the mass times the velocity. Very straightforward. And of course the kinetic energy is a half mv squared. Remember its velocity, that's important because direction matters. Let's take this car 2 example here. Inelastic, just as one example. Inelastic moving targets. Inelastic means you want the Velcro. You've got Velcro here, and the Velcro joins the cars together. So we want those facing. I'm going to make this one slightly heavier. Good. Okay. Now with this one, because we have incoming and outgoing, we're actually going to have to set the box to read 4 readings. So let's just go through that again. Once you've got a set of readings, of course, you can select your mode. Let's select your speed, enter, select the number 4, enter, mask size again 10, enter, go when ready. So I want these on either side. I want an initial speed inbound and then a final speed exit. Didn't quite get it that time. Let's try again. So let's go again, a little bit fast this time. Friction's having a bit of a problem, so we need to make it slightly faster. We'll try one more time. That's better. So we had inbound had a velocity of 1.641. And a velocity of 1.77. Of course, we want this as a minus because it's going the other way to that way. It's probably best that we say that this is positive. You can choose either direction, but make sure you're consistent. And the velocity afterwards was minus 0.234. There's going to be big experimental errors with this one. But nonetheless, bear in mind, well, let's do the momentum first. I've already preempted a large experimental error already. Let's take the first one, car 1, which was 0.5 kilograms. Car 2 was 1 kilogram because we had added the extra weight on it. 1 and 2 was 1.5 kilograms. Let's see what we get. Momentum of 4. So 0.5 by 0.82 inbound minus 1.77 by 1 minus 1.77 this way. So the total here will be minus 0.95. What's happening afterwards? Well, 1.5, which is my total mass of them moving, by minus 0.234 gives me 1.2 minus 1.26, so minus 1.26 afterwards. It's sort of equal. I mean, not only, ultimately we were expecting to be equal, but not only is there a friction problem here, but also that collision, it's flexing, it's heating up the joints, etc., etc. Nonetheless, what we ought to do with the inelastic collisions is try these. Remember, the only difference between this and GCSE level is you're going to have to select the number of speeds you're inbound, it bounces, it goes out, so you're going to select 4 readings on this machine. Once you've tried experiment 1 and experiment 2, you're then going to try experiment 3 and 4, which is elastic. This time, you want these out. You want inbound, see what happens, and then you want together and away from each other. And see if the kinetic energy is conserved before or after the collision. Ultimately, kinetic energy ought to be conserved with elastic collisions, but that would be perfectly elastic, and even this, though it looks bouncy, that doesn't necessarily mean it's perfectly elastic. So there will be a subtle difference. However, with inelastic, you would definitely see that kinetic energy is not conserved. To give you an idea of a model set of results, here is one of them, inelastic collisions. Just in case you don't get a model set of results, and we can see that this is fairly consistent, fairly consistent. The kinetic energy, on the other hand, is grossly different. For this one, definitely. A little less so there. No, hugely different. Sorry, as a decimal place out. So I'll hold it there, or press pause to copy those answers down. Whereas for the elastic collisions, let's take a look at what's going on. The momentum, that's fairly close. That's fairly close. It's closer, same order of magnitude, but this is quite a long way out. It's lots of interactions happening in this one, so it's tricky. Once again, if you want to copy those results down, press pause. Okay, I hope that all makes sense.